Okay, go. Cool.
With previously cutting-edge technology becoming cheaper and more accessible, consumer-grade biofeedback devices have flooded the market. From devices like the Fitbit wristband to a variety of smartphone applications, the sensors used to collect and analyze physiological data have shrunk considerably over the years into very non-intrusive form factors with excellent battery life, which are capable of collecting data all throughout the day. The biofeedback device that piqued our interest was the MindWave Mobile by NeuroSky. The MindWave Mobile is a wireless, Bluetooth-enabled neurofeedback headset, which costs about $100. It can measure and output the EEG power spectrums, alpha waves, beta waves, etc., for 8 hours on a single AAA battery. It also has blink detection and can calculate the wearer's attention and meditation levels on a scale from 0 to 100 using proprietary algorithms embedded in its chip. Whereas more precise EEG collection methods require numerous wet, saline-based electrodes, like those pictured here, the MindWave is very light and compact. The device has a single dry electrode on a sensor arm, which rests on the forehead, and an ear clip, which contains a grounding electrode and a reference electrode, which is used to cancel out noise in the connection. The chip in this sensor module was designed for mass-market applications, and you may have even seen its use in games like Mattel's Mindflex and the Star Wars Force Trainer by Uncle Milton. Our project goal was to completely utilize the capabilities of the MindWave and create a system that would allow a user to have constant active and passive control over their home with their mind. To accomplish this, we used Microsoft's Home OS and the Lab of Things platform to create our app. The MindWave comes with a piece of software called the ThinkGear Connector, which handles syncing with the device and exposes a TCP port through which the ThinkGear communications protocol can be used to request JSON data packets from the headset. Here is what one such packet looks like. The first thing that we did was to write a simple driver which interfaces with this port and exposes some basic roles to our app, like getAttention_level, which returns the user's current attention level parsed out of the most recently collected JSON packet. This made it simple for the app to obtain the headset data from the driver and process it to determine how to respond to the user's current mental state. The next thing we needed was a way to control devices around the house. For this, we used an Aeon Labs Z-Wave dongle called the Z-Stick 2, which uses the low-power Z-Wave spectrum to wirelessly communicate with other Z-Wave devices, which in our case are two Aeon Labs smart energy switches, which can allow or cut the power to whatever device happens to be plugged into it. Here's the basic layout of how the project is set up. The MindWave collects data from the user's brain and communicates it to a computer running our app in Home OS. When the appropriate conditions are met, the app sends a command and a device name to the Z-Wave dongle, which then wirelessly transmits the command to the specified smart switch. The smart switch receives the signal and subsequently allows or cuts the power to the device plugged into it. The app's interface was very important to us since there is a lot of information to get across to the user. Here it is. The front end is written completely in HTML and JavaScript and provides a rich interface for feedback and control. The page communicates with the underlying Home OS application by using the Microsoft WCF framework to receive data for display and to send requests to activate or deactivate various settings. Let's break down the interface, starting with the device list, here. This section contains a list of all of the smart switches currently associated with the Z-Wave dongle. In this example, there is only one switch connected. In this one, there are two. The list will expand dynamically as more switches are synced to the dongle. Each device has two settings associated with it, which allows for two different forms of direct control over the devices. We call the first mode Jedi mode. Let's see how it works. In this mode, the app waits for a burst of brain activity across the entire brainwave spectrum, after which it toggles the state of the specified device. This is meant to simulate the ability to telekinetically control the devices put into that mode. We found that while it looks cool when it works, the MindWave device does not offer the fidelity we need for truly precise and reliable control. It works about 70% of the time, but because of the device's limitations, 30% of the time, you end up looking pretty silly. Now let's take a look at the other mode, called Blink mode. Blink mode was born of the fact that Jedi mode can be unreliable. This mode counts the number of blinks registered within 3 seconds, and if the threshold is met, then the device's state is toggled. Blink mode has much better accuracy with far fewer false positives and false starts than Jedi mode. It works almost every time. But if all else fails, you can also manually click the device's name to toggle its state as well. All of the other parts of the interface are for the passive control features. The only thing better than having full control over your home would be not having to control your home at all, because it already knows what you want. This is the goal of the passive control mode. If we look back at the interface in this section, we can see an hourly schedule of the current day. Here, the user can plan out their day in terms of when they want to be active and relaxed. The user clicks and drags blocks of time to mark them as either attentive time in green or meditative time in purple. Now, as the day progresses, the app will always know what the user's desired mental state is. For example, if the time is 1 o'clock, then the system knows that the user wants to be attentive. If the time is 9 o'clock, then the user wants to be relaxed. The section directly above keeps track of the total attention and meditation levels for each hour of the day. If the schedule looked like this, then we would hope that the hour totals would look something like this, where the attention level was high during the times that the user wanted it to be, and the meditation levels were high during the times they were supposed to be. Now, if we focus on the first section of the interface, we see that it displays live feedback of the user's current attention and meditation levels, which it receives once per second, and then plots on a Bezier curve in an SVG element using JavaScript. These values are the same ones being tallied behind the scenes to determine, at certain intervals, whether or not the user's attention and meditation levels are meeting the schedule's requirements. That brings us to the last section, which is the Learn States section. Just like in the Devices section, this list will also dynamically expand as the number of devices associated with the Z-Wave dongle increases. In the left column, we see a combination of the devices and their current state. In this example, there are 2 connected devices and they are both off. The current state is marked in yellow. If we turn on device 2, which happens to be this fan, then the state changes accordingly, so it displays that we are in the state where device 1 is still off and device 2 is on. To see what the right column is for, I will activate learning mode. As you can see, each state has been assigned a probability. They all start off with an equal probability, so since there are 2 devices and 4 possible combinations of them being on or off, each combination is given a 25% chance of being triggered. After some length of time, in this case 10 seconds, the application will update the probabilities and randomly select a new combination of devices to be powered based on the updated probabilities, using the following logic. If the current combination of devices being on and off did not bring the user's mental state closer to the one they specified on their schedule, then do nothing and choose again. If the current combination of devices being on and off did improve the user's attention or meditation level during a time when they wanted to be either attentive or relaxed, then each of the other combinations gives up some of their probability to the current combination. In this way, the system will keep trying different combinations until the ones that help the mental state I'm trying to optimize for most are the ones that are selected the most often. Let's try an experiment. I'm sitting at the desk, and the system is going to try and adjust the power to the light and the fan to optimize my meditation level. Finally, we have arrived at a stable state. Here are the results. The combinations of powered devices in which the fan was on were quickly eliminated because the fan was blowing in my face and made me less relaxed whenever it turned on, which is why it completely stopped being selected near the end. The lamp had little to no effect on my relaxation, so there is no preference to state 1 or state 3. We hope that this project has demonstrated that neurofeedback is a powerful source of data, which can be used effectively to dynamically create optimal environments for unique individuals.